Hello and welcome to Microprocessors Lab. In this video, we'll learn how to convert assembly code to EXE and HEX files. Objectives of this lecture: learn how program codes are compiled and converted to applications.exe, explaining system softwares used to convert ASM source codes to EXE and HEX, writing a simple code, then converting to EXE and HEX. If we look at assembly folder contents, which we mounted before at local disk C, it contains this system software: MASM, link, EXE to bin, bin to HEX. If we have assembly source code, it will pass through these steps, this sequential process, to EXE and HEX file. First of all, we have file.asm. It will be converted to object file using system software which is called MASM. This is called assembler. It will also create two optional files. One of them is list and the second is a cross-reference file. This file contains every information of source code, machine code, segments and offset address. It has all details like instructions used. If there were some errors, it will list these errors. Cross-reference file contains same information as in list file, but in binary format. This object file will be converted to executable file using links system software, or we call it linker. It will also generate two optional files, one of them called map and the second called library. EXE, as we know, it's executable file. We can run it using program loader. Map file contains starting and ending address of program code, data code, and stack and everything. Here in link process, we can add libraries also in linking. If there is external library, will be added by this step. In executable file, we can debug and run our program. If we want to run this executable machine code on a microprocessor or a microcontroller, it has to be changed to hex file, pure hex file. Hex file are hexadecimal bytes. Each hexabyte represents an assembly instruction or a number in that instruction. This EXE file will be converted to binary using EXE to bin. It's also system software. Now we have binary format, machine code in binary format, 0 and 1s. Then this 0 and 1s will be converted to hex file using bin to hex system software. By this step, this hex file can be uploaded to microprocessor kit using sender or hyperterminal or interface. This process called assembling, linking, and conversion to binary and hex. Assembly source code is a low-level language. If we have a high-level language, file.c, which is high-level language source code, this will be converted to expandable source code using preprocessor. This expandable source code contains the code of libraries. For example, if we have written hash include std input output, here the code of std input output will be added to our main source code. Also, if we have hash defined constants, will be represent its constants. After that, this expandable source code will be converted to assembly source code using compiler. Compiler is like translator. Each C language instruction, for example, cout, cin, void main, everything will be converted to assembly source code instruction like move. This assembly source code called file.s or file.asm. Then this assembly file will be converted to object file using assembler, then will be converted to executable file using linker. By this process, we have our executable file, which can be run by program. We have many types of assembler. I just brought an example, maybe it's another assembler. This process called high-level language compilation process. It goes through this step by preprocessor, then by compiler, then by assembler, then by linker. If we look at assembling process, assembly converts source program into object program if syntactically correct and generates an intermediate object file. It calculates the offset address for every data in data segment and every instruction in code segment. Then a header is created which contains the incomplete address in front of the generated OBJ model during the assembling. Assembler complains about the syntax error, if any, and doesn't generate the object model. Assembler creates OBJ, LST, and CRF files, and last two files are optional that can be created at runtime. For short programs, assembling can be done manually, where the programmer translates each mnemonic into the machine code using lookup table. Assembler reads each assembly instruction of program as ASCII character and translates them into respective machine codes. After assembling process, we come to linking. Linking involves converting of object file into executable model, which is executable machine code. It completes the address left by the assembler. It combines separately assembled object files. Linking creates exe.lib.map files among last two are optional files. For each assembly code, when we are writing an assembly code, we have to specify memory models. The traditional memory model recognized by many languages are small, medium, compact, large, and huge. Small model supports one data segment and one code segment, and most of our programs will be small and tiny model. A large model supports multiple code and multiple data segments. Medium and compact are in betweens. And the most important for us is tiny model. Tiny model programs only run under MS-DOS system. Tiny model places all data and codes in single segments. Therefore, the total program size can be only 64 kilobytes. In each of the models, you can override the defaults. For example, you can make large data far in small model, or internal procedures near in large model. File.hex is the machine code. For example, our trainer kit in microprocessors lab is MTS86C. So it needs to be converted to hex file, then uploaded to this trainer kit. Each instruction in source code will be converted to hexadecimal number or bytes. Here are the references. If you want to download their PDFs, you can download it by clicking on these links. Now we will create a simple assembly source code. This program will swap the contents of two memory locations in data segment. For example, location 400 with 401. We will open Notepad++ software. Then we will choose the language, which is assembly, and we will start writing our program. First, we will choose memory model. We will write .model tiny, which is used in MS-DOS. We will just use tiny and small models in our programs. And now we will write code segment. Now we are in code segment. We will write assume CS belongs to code, data segment belongs to code, stack segments belongs to code, extra segment belongs to code. We don't need to use stack segment and extra segment in this program, but we have written it for you further information. And now we will write our main program. We will say origin 0 hexa if we want to start from origin 0, or for example origin 100 as we want. We give it a tab to be more clear for us. And then we will write main move SI 400 hexa. Then we'll write move AL location of SI. So now AX become the data which is in memory location 400. Then we will write move, for example, the high SI plus 1. Now the high become the data of memory location 401. Then we will write move memory location of SI D high. Now memory location of 400 hexa will be D high, which was equal previously contents of memory location 401. Now we will write move SI plus 1 the contents of AL. Now memory location of 401 hexa equal the contents of AL, which was before the data of 400 hexa. By this step we have finished our coding. We'll just write code ends, then we will say end main. We'll close up our program. Now we will save our program in the folder which contains system softwares, which is assembly folder. We come to local disk C, and in folder assembly we will write S1 and we will save it. If we look at the contents, or we can just open DOSBox and we look at the contents of assembly folder, we have already S1 program, which is assembly source code. Its size is 245 bytes. So now we will assemble our source code using MASM software. We will write MASM s1.asm. Here we have object file name. We don't have to give a name because it's already given a name, which is S1. We'll just press enter. But here if we want to create list file, it's by default null. It will not create. If we want list file, we'll just give it a name. We'll say S1 lst, S1 crf. Cross-reference files, also we want to see its contents. Now if you see, we have 0 warnings and 0 errors. Everything looks fine. We don't have any error. If we had an error, it would be shown here. For example, if I put an error here and if I say DHH, by mistake I have written this, and if I save this syntax error, if I come to program again and if I say MASM s1.asm, s1 lst, s1 crf, it will give me one severe error, which is at line 9, symbol not defined DHH. This will tell me my error. Also I can find it in list file in assembly folder. This is my list file. I will just right click on it, edit with Notepad++. By the end I will have my error, one severe error, which is at line 9, symbol not defined. Now I will correct my error. I will save it again and come back to my program. I will just write MASM s1 lst, s1 crf. Now I have 0 warning error and 0 severe errors. And if we check our list and cross-reference file, we'll just right click and edit. As we said, it contains every information like our source code and machine code. For example, this move SI, it became BE, and 400 hexa, it's just written 400. For example, move AL become 8A, this belongs to this instruction, and SI, which is data, will be 4, or any other information depend on that program, which is in location 400 in data segment. This is the offset address. We have code segment. In logical address we have code segment and offset, which is IP, instruction pointer. Here instruction pointer 0 and instruction pointer 3, because we have 3 bytes in code segment. First byte, location 0, location 1, location 2, and location 3 contains 8A, which is move AL. Then location 4 is 04, the location which is specified by 400 in data segment, like this, and so on up to end. We have mappings, code segment and data segments, symbols, type, value, everything's total lines, total symbols, and its size. And now we come to next step, which is linking. We'll write link s1 dot, now it became object dot object. We'll press enter. This already will create s1.exe for me. Then I will press enter. If I want to see the map, I will say s1 map, and I will press enter. If I have an external library which adds before here, like another object from another program or library, will be added with my main program, it will extract to here, and I will give it the name, but it will tell me there is no library lib. Okay, I have finished my linking also. Now I have executable file. If I see, I have map and I have executable file s1. This application cannot be run like this. We can run it inside debug in DOSBox here. Now if I want to continue converting my exe file to hex file, I have to write exe2bin s1.exe, and I will press enter. Now I will see binary file have been created. And after this step, I will convert this binary file bin to hex, and I will give it s1.bin. So now if I see my hex file have been created, this is hex file. If I right click on it and open it, I will see my pure program. If I look at offset 0 here in list file, you will see in offset 0 I have BE 400, then 8A04 and up to end. You will see at offset 0 I have this data BE 0004, 8A04, 8A74 up to end of my program. This called machine code. This is pure machine code. Hexabytes, which will be uploaded to microprocessor RAM byte by byte. Now we come to our main program. We want to debug to run our program. We'll just write debug s1.exe. Now we are debugging our executable program. I will say u unassemble. It's already offset 0, and here's our program, which contains 5 instructions. If I want to execute this instruction one by one, I will just write R, and we'll see the first instruction which will be used is move SI 400. I will check the memory location 400 and 401 data, dump 400, 401. It has FEC4. This memory location, after executing my program, these 2 bytes will be swapped. C4 will be copied to location 400 and FE will be copied to location 401. So now I will type T, which is trace command. SI will be 400. And location of 400, which is FE, will be copied to AL. It's already written here. I'll just type T, and we'll see AL become FE, and location 401 is C4. D high will be C4. Now D high, which is C4, will be copied to location 400. Previously it was FE. In this instruction, the content of AL will be copied to this location. FE will be copied to location 401. Now we are at the end of our program, and the instruction pointer already executed up to 0D. I will check again the content of memory location 400 with 400. 1. Before it was FE C4, now becomes C4 FE. And if I want to execute my program by one instruction, I have to change my instruction pointer again to 0 offset. I will say RIP and will enter 0. I will write U0 or U, and I will see my program up to where it's finished. From offset 0 up to offset D, which is the instruction after move memory location of SI plus 1 AL. So I will execute my program from offset 0 up to offset D. Offset D will not be executed, but all instructions before it will be executed. So now if I want to execute this code by one instruction, I will just say G equal CS0 up to D, and I will press enter. So now our memory location exchange have been executed. If I check again, memory location 400, 401, it become FE C4.